Welcome to this coding walkthrough. In today's session, we'll tackle the problem of performing a level order traversal on a binary tree. This is a classic problem that tests your understanding of tree data structures and traversal algorithms. Let's dive in and explore efficient ways to solve it. In this problem, we are tasked with performing a level order traversal of a binary tree. This means that, given the root of the tree, we need to traverse the nodes level by level, from left to right, and return their values as nested lists. The input to the problem is the root of a binary tree, where each node is defined by a class that has a value, a left child, and a right child. The output should be a list of lists, where each inner list represents the node values at a specific level in the tree. When performing the traversal, the nodes at each level should appear in the order they are encountered, moving from left to right. Let's look at an example to make this clearer. Imagine we have a binary tree with the root node having a value of 3. The root has two children, 9 on the left and 20 on the right. The node 20 further has two children, 15 on the left and 7 on the right. The output for this tree would be a list of lists, 3, 9, 20, 15, 7. Each inner list corresponds to a level of the tree, starting with the root, followed by its children, and so on. To break this example down further, at level 0, we have the root node with a value of 3, so the first list is 3. At level 1, the left child of the root is 9, and the right child is 20, forming the list 9, 20. Finally, at level 2, the left child of 20 is 15, and the right child is 7, resulting in the list 15, 7. In another simpler example, if the tree contains only a single node with a value of 1, the output would be 1, as there is just one level containing the root node. Now consider the case where the tree is empty. In this scenario, the input root is none, meaning there are no nodes in the tree. As a result, the output for the level order traversal would simply be an empty list. The constraints and examples provided help clarify how to handle various tree structures, from complex trees with multiple levels to edge cases like empty or single-node trees. The problem also specifies some constraints and edge cases to keep in mind. First, the number of nodes in the tree can range from 0 to 2000, so the solution needs to handle larger trees efficiently. Additionally, the values of the nodes can range from -1000 to 1000, meaning the solution must account for negative values in the tree. Key edge cases include empty trees, where the output should be an empty list, and single-node trees, which should return a list containing just the root's value. By considering these constraints and edge cases, we can ensure our solution is robust and handles all possible inputs correctly. To solve the problem of performing a level order traversal on a binary tree, we started by considering a recursive depth-first search approach, or DFS. With this method, the idea is to use recursion to traverse the tree while keeping track of the depth of each node. At each level, we add the current node's value to a list that corresponds to its depth. This is done by maintaining a list of lists, where each inner list represents a specific level of the tree. The process involves creating a helper function that takes in the current node, the depth, and the result list. As we traverse the tree recursively, we append each node's value to the appropriate list based on its depth. While this method is intuitive and uses minimal additional data structures, it does have some downsides. For example, it can lead to stack overflow issues for very deep trees and may be harder to debug or visualize compared to iterative methods. Furthermore, it doesn't strictly follow a level-by-level traversal order as seen in breadth-first search, which makes it less aligned with the problem's requirements. Next, we considered an iterative breadth-first search approach, or BFS, which uses a queue to perform a true level-by-level traversal of the binary tree. In this method, we start by initializing a queue and enqueuing the root node. As we process the tree, we handle all nodes at the current level by dequeuing them, collecting their values, and enqueuing their children. The values for each level are stored in a separate list, which is added to the result list. This process continues until the queue is empty, at which point all levels have been processed. The iterative BFS approach has several advantages. It naturally follows the level-by-level traversal order, making it easier to debug and visualize. Additionally, there's no risk of stack overflow since it doesn't rely on recursion. However, one trade-off is its memory usage, as the queue can grow to store all nodes at the widest level of the tree. Despite this, it remains an efficient and straightforward solution to the problem. Another approach we briefly considered is a variation known as zigzag level order traversal. This method involves traversing the binary tree level by level but alternating the order of traversal between left to right and right to left on each level. While this is an interesting variation, it's not required for this particular problem, as the prompt does not ask for any alternating order. The additional complexity of implementing a direction flag in the BFS approach makes this variant unnecessary here. Ultimately, we chose the iterative BFS approach as the most direct and efficient strategy. It avoids the limitations of recursive DFS, such as Stack Overflow, and produces results that align perfectly with the problem's requirements. Additionally, its iterative nature makes it easier to implement, debug, and understand. There were some key observations that helped solidify our strategy. First, the structure of a binary tree is inherently suited for level order traversal using a queue. This is because the parent-child relationship in a tree mirrors the first-in, first-out nature of a queue. Recognizing this natural alignment was an important aha moment in selecting BFS as the preferred method. On the other hand, while recursive DFS is technically feasible, it doesn't inherently lend itself to level-by-level processing. Instead, its recursive nature makes it better suited for depth-oriented tasks rather than breadth-oriented ones. With BFS, the process is highly efficient because, at each level, the number of nodes processed corresponds exactly to the number of nodes at that level. This ensures that the approach scales well for different tree structures while maintaining clarity and simplicity in implementation. When comparing DFS and BFS, there are a few key trade-offs to consider. Recursive DFS has an elegant and concise implementation, but it risks stack overflow for deep trees and requires additional effort to ensure level-specific lists are maintained. Iterative BFS, on the other hand, avoids these risks and is more intuitive for level-wise processing, though it does require memory for the queue. In terms of memory usage, BFS does require additional space proportional to the width of the tree, which is the maximum number of nodes at any level. However, this is generally manageable and a worthwhile trade-off for its safety and clarity. Both DFS and BFS have a time complexity of O(n), where n is the number of nodes in the tree, but BFS often performs better in practice due to its iterative structure. Overall, BFS is the most suitable approach for this problem because it aligns well with the problem constraints, avoids recursion-related risks, and is straightforward to implement and debug. To perform a level order traversal of a binary tree, we use a breadth-first search, or BFS, approach. This method processes nodes level by level, starting from the root and working downward. First, we initialize two things: an empty list called result to store the final traversal, and a queue to help manage the nodes we need to process. The queue is a first-in first-out structure, ensuring that nodes are processed in the correct order. Initially, we add the root node to the queue. Before diving into the main logic, we handle an important edge case. If the tree is empty, meaning the root is none, we immediately return the empty result list. Once the tree is confirmed to be non-empty, we enter the outer loop. This loop continues as long as there are nodes in the queue. At the start of each iteration, the queue will contain all the nodes at the current level. This ensures we process one level at a time without mixing nodes from different depths. Within the outer loop, we focus on processing a single level of the tree. To do this, we first determine the number of nodes at the current level, which we call level_size. This is simply the size of the queue at that point. Knowing the level_size helps us isolate the nodes at the current level and avoid mixing in nodes from subsequent levels. We then create an empty list called current_level to store the values of nodes at this level. Next, we enter the inner loop, which runs exactly level_size times. For each node in the current level, we dequeue it from the front of the queue and add its value to the current_level list. If the dequeued node has a left child, we unqueue that child. Similarly, if it has a right child, we unqueue the right child as well. By the end of the inner loop, all nodes at the current level will have been processed. At this point, we append the current_level list to the result list. The outer loop then repeats, processing the next level of the tree in the same way, until there are no more nodes left in the queue. This algorithm has several key insights that make it efficient and reliable. Using a queue ensures that nodes are processed in a breadth-first manner, which is essential for level order traversal. The use of level_size guarantees that nodes from different levels are not mixed during processing, preserving the grouping of nodes by their depth in the tree. Handling the edge case of an empty tree right at the start prevents unnecessary computation and avoids potential errors. In terms of efficiency, the algorithm processes each node exactly once, performing a constant amount of work per node for operations like enqueuing and dequeuing. This gives it a time complexity of O(n), where n is the total number of nodes in the tree. The space complexity depends on the maximum number of nodes at any level, which is proportional to the width of the tree. In the worst case, for a balanced tree, this width is approximately half the total number of nodes, resulting in a space complexity of O(n). The two primary data structures used are the queue, for managing nodes to process, and lists, for storing the node values at each level and the final result. To help visualize this, consider the binary tree shown here, where each level is distinct and well-defined. Let's walk through the algorithm step by step using the given binary tree. Initially, the result list is empty, and the queue contains only the root node, which is 1. At the first level, the current_level list will contain just the value 1 since that's the only node at this level. We then enqueue its children, 2 and 3. After processing level 1, the result becomes 1, and the queue contains nodes 2 and 3. At the second level, the current_level list will include 2 and 3, as those are the nodes at this depth. We then enqueue their children, 4, 5, and 6, now the result becomes 1, 2, 3, and the queue contains nodes 4, 5, and 6. At the third and final level, the current_level list contains 4, 5, and 6, since these nodes have no further children to enqueue. After processing this level, the result becomes 1, 2, 3, 4, 5, 6, and the queue is empty. With no more nodes to process, the algorithm outputs the result, which correctly represents the level order traversal of the tree as 1, 2, 3, 4, 5, 6. The Python implementation of this algorithm is both concise and easy to follow. We first handle the edge case where the tree is empty by checking if the root is none. If it is, we return an empty list. Otherwise, we initialize the result list and a queue, using Python's collections.deque for efficient FIFO operations. The outer loop runs as long as the queue is not empty. At the start of each iteration, we determine the level_size, then initialize the current_level list. The inner loop iterates level_size times, dequeuing nodes, adding their values to current_level, and enqueuing their children if they exist. After processing all nodes at the current level, we append current_level to result. Once the queue is empty and all levels have been processed, we return the result list. This implementation is efficient, with a clear structure that matches the step-by-step explanation of the algorithm. To implement the level order traversal in Python, we start by importing the deque class from the collections module. This will help us efficiently manage the queue structure we need for the traversal. Next, we define a tree node class to represent each node in the binary tree. Each node has a value, as well as pointers to its left and right children, which default to none if not provided. After that, we define the solution class, where the level order method will perform the traversal. The first thing we handle is the edge case where the tree is empty. If the root is none, we simply return an empty list. Assuming the tree is not empty, we initialize an empty list called result to store the final output and a deque called queue, which we seed with the root node. The while loop is used to process the tree level by level as long as there are nodes in the queue. Inside the loop, we first create an empty list called level to store the values of nodes at the current level. Then, we use a for loop to iterate over all nodes currently in the queue, which represents the nodes in the current level. For each node, we remove it from the queue using popleft and add its value to the level list. If the node has a left child, we append it to the queue, and similarly, if it has a right child, we append that as well. This ensures that all children of the current level are added to the queue for processing in the next iteration. Once we've processed all nodes at the current level and built the level list, we append this list to the result. This completes the processing of one level, and the loop continues until the queue is empty, meaning all levels of the tree have been traversed. Finally, after the while loop finishes, the result list, which now contains the values of all nodes grouped by their respective levels, is returned. This completes the level order traversal, giving us a list of lists where each sublist represents the values at one level of the binary tree. Here, we start by defining the treeNode class, which represents the structure of a binary tree node. Each node contains an integer value, a reference to the left child, and a reference to the right child. The class also includes multiple constructors to create a node with or without child nodes. Next, we define the solution class, where our main method for solving the problem resides. The level order method takes the root of the binary tree as input and returns a list of lists, where each inner list represents the values of nodes at a specific level of the tree. The first step in the method is to handle the edge case where the tree is empty. If the root is null, we simply return an empty list since there are no levels to traverse. Then, we initialize the result list to store the level-wise traversal and a queue to perform a breadth-first search. The root node is added to the queue to kick off the process. Now, we enter a while loop that continues as long as the queue is not empty. This ensures we process all levels of the tree. At the start of each iteration, we create a new list to store the values of nodes at the current level. We also determine the number of nodes at this level by checking the size of the queue. Then, we use a for loop to process each node at the current level. Inside the loop, we remove a node from the queue and add its value to the current levels list. If the node has a left child, we add it to the queue. Similarly, if it has a right child, we add that to the queue as well. Once all nodes at the current level are processed, we append the level list to the result list. This process repeats for all levels of the tree. Finally, when the queue is empty, meaning we've traversed the entire tree, we return the result list containing the level order traversal. Let's start with the first example, a simple binary tree. The input tree has a root node with the value 3, which has two children, 9 on the left and 20 on the right. Node 20 further has two children, 15 and 7. To perform a level order traversal, we first initialize an empty list called result to store the final output and a queue to help us process each level of the tree. The root node, which is treeNode with value 3, is added to the queue. Now, we process the first level. We initialize an empty list called level to hold the values at this level. Since there's only one node in the queue, we loop once. We remove the node from the queue, which is treeNode with value 3, and add its value to the level list. At this point, the level list contains 3. After processing the root node, we add its left and right children, treeNode with values 9 and 20, to the queue. With this, the first level is complete, and we append the level list, which is 3, to our result, making result equal to 3. Next, we move on to the second level. We initialize a new level list and loop through the nodes in the queue, which now has two nodes, treeNode with values 9 and 20. First, we process the node with value 9. We remove it from the queue, add its value to the level list, and check its children. Since it has no children, the queue remains unchanged. Then, we process the node with value 20, removing it from the queue and adding its value to the level list. This makes the level list 9, 20. We then add its left and right children, treeNode with values 15 and 7, to the queue. After appending this level list to result becomes 3, 9, 20. Now we process the third and final level of the tree. We initialize an empty level list and loop through the two nodes in the queue, which are treeNode with values 15 and 7. First, we process the node with value 15. We remove it from the queue, add its value to the level list, and check its children. Since it has no children, the queue remains unchanged. Next, we process the node with value 7, removing it from the queue and adding its value to the level list. This completes this level, with the level list now being 15, 7. We append this level list to result, giving us the final output of 3, 9, 20, 15, 7. This completes the level order traversal of the first example. In the second example, the tree contains a single node with the value 1. We initialize the result list to an empty list and add the root node, treeNode with value 1, to the queue. Now, we process the first and only level of the tree. We initialize an empty level list and loop once, as the queue contains just one node. We remove the node from the queue, which is treeNode with value 1, and add its value to the level list. Since this node has no left or right children, the queue remains empty. After appending the level list, which is 1, to result, we get the final output, 1. This completes the level order traversal for the second example. In the third and final example, we are given an empty tree, where the root is none. To handle this edge case, we start by checking if the root is null. Since it is, we immediately return an empty list as the result. The final output is simply an empty list. This concludes the solution walkthrough for binary tree level order traversal. The time complexity of the binary tree level order traversal algorithm is O(n), where n represents the total number of nodes in the binary tree. This is because every node in the tree is processed exactly once. Specifically, each node is enqueued into the queue and dequeued from the queue once, resulting in a total of n enqueue and dequeue operations. Since each of these operations takes constant time, O(1), the overall cost for processing all nodes is O(n). Additionally, the algorithm involves a while loop that iterates once for each level of the tree. Within this loop, a nested for loop processes all nodes at the current level. While the number of outer iterations depends on the height of the tree, the total number of inner iterations across all levels is still proportional to n, as every node is only processed once. Therefore, regardless of whether the tree is balanced or unbalanced, the dominant factor remains the processing of n nodes, leading to an overall time complexity of O(n) in all cases. The space complexity of this algorithm is O(w), where w is the maximum width of the binary tree, which is the largest number of nodes at any single level. This is primarily driven by the space required for the queue. As the algorithm processes each level, the queue holds all the nodes for the current level, and its size can grow to the maximum width of the tree. For a balanced binary tree, this width is approximately O(n/2), which simplifies to O(n). For an unbalanced tree, the width can be smaller, but in the worst case, the space complexity is still O(n). Additionally, the result list stores all node values grouped by their levels. Since there are n nodes in the tree, the space required for the result list is also O(n). Thus, the total space complexity is determined by the larger of these two factors, which is O(n) in the worst case. The algorithm also uses a small amount of auxiliary space for variables such as level and node. These require constant space and are negligible compared to the space used for the queue and result list. As a result, they do not affect the overall space complexity. When comparing this approach to a naive depth-first search (DFS) solution, the BFS-based approach proves to be more efficient. A naive DFS might involve storing nodes in a dictionary grouped by depth, which would require additional space for the dictionary and might involve revisiting nodes multiple times. In contrast, the BFS approach ensures each node is processed exactly once, making it optimal in terms of both time and space efficiency. This combination of single traversal and efficient space usage highlights the advantages of BFS for level order traversal. In terms of best, average, and worst-case scenarios, the algorithm demonstrates consistent performance. In the best case, where the tree is empty, the algorithm completes in O(1) time and uses O(1) space. For a typical balanced binary tree, the average case time complexity is O(n), and the space complexity is also O(n). Even in the worst-case scenario, where the tree is completely skewed and resembles a linked list, the algorithm still runs in O(n) time and uses O(n) space. Mathematically, the time complexity can be understood by summing the work done at each level. Since the total number of nodes across all levels is n, the total work is O(n). Similarly, the largest space requirement corresponds to the widest level of the tree, which, in the worst case, is also O(n). This consistency across all cases showcases the efficiency and scalability of the algorithm. When tackling binary tree level order traversal, there are a few common mistakes to watch out for. First, failing to account for null or edge cases can cause significant issues. For example, if the tree is empty or consists of a single node, not addressing these scenarios might lead to null pointer exceptions or incorrect outputs. Always include a base case to return an empty list or equivalent value when the root is null. Next, traversing child nodes in the wrong order is a frequent pitfall. Since level order traversal expects nodes to be processed from left to right, using a queue and consistently enqueuing the left child first, followed by the right child, ensures correctness. Finally, some might attempt to use a depth-first search approach for level order traversal but forget to track the depth to group nodes by their respective levels. To avoid this, pass depth as an argument to the recursive function or maintain a global structure that maps levels to their corresponding nodes. Memory inefficiency during BFS is another area where mistakes can occur. For instance, enqueuing null children or neglecting to dequeue processed nodes can lead to unnecessary memory consumption. To resolve this, avoid adding null nodes to the queue and ensure you promptly remove nodes that have already been processed. Another challenge arises with large trees. In these cases, unoptimized solutions may hit recursion depth limits in DFS or excessive memory usage in BFS. To handle this, favor an iterative BFS approach, which avoids recursion depth issues, and optimize memory by processing each level fully before moving to the next. This ensures your solution remains efficient even for very large datasets. Understanding level order traversal as a fundamental breadth-first search problem is key to excelling in interviews. Mastering the queue-based approach is essential, as it forms the foundation for variations like zigzag traversal, bottom-up level order, and vertical order traversal. From a space complexity perspective, BFS typically requires O(n) space for the queue, while DFS can be optimized to use O(h) space, where h represents the tree height. Interviewers often ask about these trade-offs, so be prepared to discuss them. Additionally, follow-up questions might include variations like calculating level sums, identifying the maximum value at each level, or handling incomplete binary trees. Lastly, always ask clarifying questions about the problem, such as whether the tree can be empty or if node values are unique. This demonstrates your attention to edge cases, which is highly valued in interviews. Level order traversal is closely related to several other problems that you may encounter. For example, the binary tree right-side view problem, LeetCode 199, shares a similar BFS structure but requires you to track the last node at each level. Another variation is binary tree zigzag level order traversal, LeetCode 103, which adds complexity by requiring an alternating traversal direction at each level. Then there's binary tree vertical order traversal, LeetCode 987, where nodes are grouped by vertical columns instead of levels, presenting a unique twist on the basic approach. Lastly, the maximum width of binary tree problem, LeetCode 662, involves using level order traversal to calculate the maximum width of the tree based on node indices. These problems highlight how foundational level order traversal is and how it can be adapted for various scenarios. When solving level order traversal problems, you can choose from a few alternative approaches, each with its own trade-offs. Recursive DFS is simpler to implement for small trees but can run into recursion depth limits for large or skewed trees. This method is best used when the tree height is small or the constraints are loose. Iterative BFS, on the other hand, is more robust for large trees and avoids recursion limits, but it can consume significant memory if the tree is very wide. This approach is the most commonly used in practice and is well suited for general use cases. Another option is pre-ordered DFS with level tracking, where you explicitly use a stack to manage iteration and avoid recursion depth issues. This method is beneficial when BFS is impractical due to space constraints, particularly if the tree is balanced. Each of these methods has its place, and understanding their strengths and weaknesses will help you choose the right one for a given problem. Great job! We've successfully walked through the binary tree level order traversal problem and discussed an approach to solve it. Remember, binary tree problems are a great way to sharpen your problem-solving skills. Thanks for joining us, and we'll see you next time for more coding solutions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!